Hi everyone, welcome to our final project about deformable object manipulation. Here's our table of contents. First, folding a deformable object is hard because it has high dimensional configuration spaces and its behaviors are very unpredictable because they are soft. So our goal in this project is to achieve folding it by geometric vision, deformable body modeling, motion planning, and compliant control. Next is our methodology. In this project, we used a simulation environment similar to Drake. This environment has a Frank's pandas arm and the gripper that has degree of freedom of 7. That is the same as the EVA 14 arm we used in class. We do not use Drake here because Drake's better at rigid body dynamics, but the dynamic closed folding environment is better on soft bodies, which is more feasible for our project. It is still similar to Drake that it uses modular structure programming and can implement FK, IK optimizations, etc. Our goal in this project is to fold upper left corner to the right along the same upper edge, which we broke down to 4 stages: pre-grasp, grasp, fold, and release stages. Here's a picture of the 4 stages. In the planning and control section, we have IK for trajectories planning and a compliant control for softer and more stable touches that are important for deformable object folding. In the vision section, we first grayscale the RGB image taken by the implemented camera. Then by the darkness difference between the fabric and the table, we identify the corner points of the fabric. Then we put the 4 points into a coordinate system so we can know their locations and which point is for grasping and for folding. If the size of the fabric changes, the locations of the points will change, but the relationships stay the same. So we apply the 0.25-meter fabric coordinate to the new coordinate to find the ratio, then apply back to the motion and control module, achieving points mapping. Here are the figures before and after points mapping. Finally is the experiment setup. In experiment 1, we keep the size for the fabric same and its corner points known. Then we generate 10 random environments for testing. In experiment 2, we keep the environment same but change the fabric sizes to test our vision functionality.
Now I will briefly present our experimental results and the key discussions. In experiment 1, we randomly generated 10 different environments. This figure summarizes the visual results of the 10 experiments. The results show that 7 out of 10 trials are successful, giving a 70% success rate. The failure cases happen at different stages, including pre-grasp, folding, and release, meaning that the errors are not concentrated in a single phase. Overall, this experiment shows that our planning and control pipeline alone is already capable of performing stable closed folding. In experiment 2, we introduced the vision module and tested 10 different fabric sizes. The results show that 9 out of 10 trials are successful with a 90% success rate. Only the smallest fabric fails due to inaccurate corner detection during folding. These results demonstrate that our vision-based perception integrates well with the planning and control system and generalizes across different fabric sizes. Comparing the 2 experiments, we observed that success rate increases from 70% to 90% after introducing vision. This suggests that under our current setup, the interface between geometric vision and compliant control is both stable and reliable. We also observed that larger fabrics require a longer folding time, since longer trajectories are needed under a fixed control frequency. After adding vision, the main system bottleneck shifts from control to perception accuracy. Our main strengths are first, the clear modular pipeline of vision planning and control. Second, the system shows strong generalization across fabric sizes. Third, impedance control ensures safe and stable interaction with deformable fabrics. However, our limitations are that we only fold square fabrics now. The vision module is sensitive to noise, and the system only supports single-step folding. For future work, we plan to extend to real garments, introduce closed-loop vision and force feedback, and support multi-step folding pipelines. Overall, this project shows that integrating perception, planning, and control is both feasible and effective for deformable object manipulation.
Here's our acknowledgement. And that's all for our presentation. We would like to thank all the core staffs and the professor for the help on this project and throughout this semester. Thank you. Here's our reference.